All right, I would like to introduce right now Bryan Singer, the CTO of Red Trident. He's going to be giving a presentation on safety instrumented systems, very much in context, thanks to the Triconics hack of this past year. So I give it to you.
Thank you very much. All right. Well, good morning or almost good afternoon. I probably don't even need the microphone here. You guys hear I have the nice drill sergeant's voice left over from my time in the Army. So yes, today we're going to be talking a little bit about safety instrumented systems, and really, I was asked to talk about SIS, but I really went back and said, fundamentally, I need to talk about safety on the whole, so everybody understands kind of the context of why we have SIS systems and how that relates to safety and security. Those that know me know I really don't like to let anything lie, especially anything really stupid. And I heard something said one day that I thought was actually really silly, which was our safety systems will protect us. That'll keep us from being hacked. And this is after I'd spent quite a bit of time going after these devices and knew better. So I actually went out and built a company around the whole idea. Our presentation is not up here? It's on through. Okay, it's there. Sorry. Okay, my mistake. Okay. So yes, just a really quick introduction. Those that know me, I've been around for quite a while in this field. A lot of time in plants. I also did a lot of penetration testing, vulnerability assessments. I kind of lived at the plant level for quite a while. And again, around this whole concept of safety instrumented systems, I built an entire company around this, focusing for about 8 years. I mean, that was the main thing I wanted to look at. I've co-authored a couple of books in this space as well, and I've been to S4 a number of times. So I've been around a little while. So we'll start out with talking, when good equipment goes bad, the concept of safety. Machines break. People break, either intentionally or unintentionally. People do silly things sometimes. And I always said, and the bad joke of the day is, if you invent something that's idiot-proof, the world will invent a better idiot, right? So, so you understand that things are not always going to go as we wish them to. Equipment breaks. Bottom line is, get over it, okay? I don't care what vendor you are. I don't care what equipment you make. Eventually, something's going to go wrong. Or people are not necessarily going to use your equipment the way that you want them to, okay? So a couple of ground rules. I'm not going to talk about any vendors. And in fact, if I mention one, it's going to strictly be by accident. I'm really avoiding the vendor discussion today. I'm not here to call anybody under the carpet, because there are some vendors that are pushing some things I'm directly going to counter, and I'm going to talk against, okay? That said, I'm not trying to call any vendor onto the table. Every vendor has implemented their solutions a little bit differently. I'm always going to say you should defer to your vendor when it comes to implementing their technology, but hopefully at the end of this presentation, you'll have an idea of the kinds of questions to ask that you're going to need a vendor to actually demonstrate to you, okay? So we're going to stick to fairly generic safety terms as well. I realize that there are different terminologies out there. People implement things differently. Plants have different processes. I'm going to try to stick to general terminology. And again, at the end, I'm going to give you a few questions that no matter what type of an environment you walk into, you should be able to ask these questions and get a meaningful discussion to come back, right? So some key concepts here we'll talk about. Some failure modes for industrial control systems that we want to keep an eye on, okay? These are 4 categories of the ways the plants go down. So ideally, one of the questions I ask on plant assessments, one of the first questions I ask is, what is your planned versus unplanned downtime window look like? What do your planned versus unplanned ratio look like? Okay, planned downtime, not a bad thing. Okay, we say, hey, we're going to shut down for 3 weeks. That's built into the schedule. Everything's built on. Everybody understands that's coming. Not a big deal. It's the unplanned maintenance that's the problem. That's when you have issues that actually go wrong on the plant, machine breaking, product quality issues, all kinds of things like that. And when I see a company or I go into a customer that has a very high amount of unplanned downtime, that's the first indicator to me that they probably have mechanical integrity issues within the facility. All right, that they have something going wrong. They may have process problems within the facility, or operator training problems, or something of that nature. But that's the first question I look for. So some things here that we look for. What I categorize as intermittent failures. These are corrected by logic conditions in the system. An example, let's say we're doing a finished packaged goods, like maybe we're making a kid's drink mix or a soup box or something like that. And there's logic in there that says if the weight is not high enough in the package, reject the package, right? That's kind of an intermittent failure. Something's wrong in the process, okay? Minimal to no process interruption. So the only thing you're probably doing is increasing your cost to produce a little bit, okay? Nuisance trips. Nuisance trips is what we like. A lot of people like to say, oh, well, the plant just shut down. Well, nuisance trips by and large are exactly that. They are a nuisance. But that is where there is some condition within the process that has been measured, and it says, hey, we're going to shut down to a safe state, or something goes wrong with a particular controller. And again, really, it's not a dangerous failure. The safe state is maintained. But everybody, and here's the first problem that I bring back to people when they start saying that our safety will take care of us from security threats, all right? They're like, oh, all you're going to do is create a nuisance trip. Okay, great. You're right. All I can do is create a nuisance trip. Now I'm going to write logic bomb inside of your database that is going to trip off in a stored procedure, update another system, and it's going to do it randomly about 6 times a day, okay? Now ask me whether or not that nuisance trip is a big issue from a security standpoint. So even though it's only a nuisance trip and I'm not going to hurt anybody, I can still have a significant impact if the only thing I can do to a system is cause a nuisance trip. So don't just use that as an excuse to dismiss doing your cybersecurity. Okay? Next, we get to unplanned outages. This is where the nuisance trips actually go into some type of sustained failure. You might have a mechanical break. An example here might be lubrication schedules that weren't kept up to date, or a condition-based monitoring program did not measure, that wasn't responded to in time, and now you've had a mechanical failure and a big part of your process is broken down for quite a while. Right? Or maybe I was at a power generation facility one time, and a piece of the building just fell off, right? Or I walk in the next morning, they say, we're going to be down for several weeks. What? Well, the conveyor got hit by a piece of the building that really just fell off. We're down, right? That's an unplanned outage, okay? They weren't planning on this one. And then we get into the worst category, which is actually kinetic and safety impacts or dangerous failures, okay? Now, I want to make sure we're really clear here about safety. Safety, hold on just a minute, okay? Don't anybody throw anything at me. Safety, by and large, only deals with one thing: entropic hardware fault, okay? In other words, it is something happens. It's mechanical. It's not deterministic in nature. Now, I realize all the safety standards say, yes, we deal with systematic fault. Yes, we address security. And I look back at them and I say, no, you do not, right? They all say in there in one line, you need to be cyber secure. Boom, that's it, okay? Now, some of the standards are starting to adopt that a little bit. But process safety, by and large, is just meant for entropic hardware fault, simple things like that, random acts of nature, okay? But process safety is the process of identifying the probability, again, entropic hardware fault, of failures in equipment and machinery that could result in damage to personnel or equipment, and then reducing that probability to acceptable levels. That's it. It's all math. Okay? So you go in and you do a study, you do a HAZOP study, a hazards operability study, you do a process hazards analysis, you go and you do cause and effect diagrams, modeling all the different things that can happen in a process, and you measure what is the probability of this piece of equipment or this system or this component failing. What is the probability per hour? We call it the probability of failure on demand. What is the rate of occurrence per hour that we expect this device to fail? Okay? Now, you can do that by testing the device. You can hammer the device for a whole long time or leave it out there running. I mean, think about it. If a vendor sells 35,000 SIS systems and they deploy them all over the world or something like that, it's not going to be long before they're going to start getting some feedback about how often those components fail. They can work that back into their equations. Or just from an engineering, design, and testing perspective, they can measure what this failure is. Again, probability of random hardware fault for the most part. But then designing the system to reduce that probability of failure per hour to an acceptable level. That's the whole SIL concept, which we'll talk about. Primarily just entropic hardware fault. What you're doing, safety instrument, something that got said at this show, and I'm not sure if the individual's here, I don't want him to be embarrassed, but I'll mention it, is, right after I'd started doing a lot of this research, somebody goes, he was a researcher in the community, and goes, oh, well, hey, when the process controller sends the command to the safety system to implement its function, and that was like fingernails down the technical chalkboard for me. I'm like, whoa, that's not how these things work. And he was doing research on these components at this point. But when we talked to him a little bit, I'm like, look, safety instrumented systems monitor the process. They don't interact with the PLC by and large. Now, I know there's some exceptions in there in the vendor world, but the safety system monitors the process conditions, and it looks for unsafe conditions, and it tries to resolve them. Okay? So how is this managed? Safety on the whole combines physical infrastructures and safeguards. Okay? Process control logic, what we call soft interlocks. Right? So a soft interlock would be an example. In your PLC says if temperature sensor is greater than 200, then you want to reduce the burner or something like that. Or if machine speed is greater than some speed, you want to reduce the machine speed. And those are overly simple, but the idea is that you have logic inside of your ladder logic or program or function blocks or whatever. You have logic in there that measures the process conditions and says, well, that's more than we want it to be, or that's less than we want it to be, so change these things. That's an example of a soft interlock. A better example would be I was working on a conveyor system with engines that were on big carts, and they were moving, right? And so there was a light curtain between these two. This is where you're going to hear the issue, the first security issue that comes up. There was a light curtain between those two. And the idea would be somebody would come up and the cart would stop. They would walk all the way around the cart, make a bunch of changes, right? So the light curtain would say there's somebody standing between these two engine carts. And if that condition was true, then it would not advance the next cart. Problem was, there was too much network traffic in the area at that particular time, okay? The signal that there was somebody standing there was never received by the process control device. Bad logic, don't get me wrong, but the signal was never received. Carts moved at an unexpected time. The woman was crushed between them. Okay, now, thankfully, she actually just survived that one with some minor injuries, but it was an example of where soft interlocks can have bad impact and bad consequence. Right? Then we went and said we have physical safeguards, and this is like burst discs. In other words, pressure gets too high in the vessel and it bursts, right? You saw the explosions that happened up in Boston recently, right? All the gas explosions. What happened in that deal? Well, there was so much overpressure. So you have burst disc or you have vent discs at the end of each one of those houses out there, right? It's there in case there's too much pressure on the line, but it's there in case there's just a little bit too much pressure on the line. When there was a whole lot of extra pressure on the line, all those vents and all those houses over a huge area, they basically opened up at the same time, allowing a lot more gas to flow in there. And so guess what? All it took was a triggering event. Again, this is where you look at it and say, well, under nominal conditions, this should be safe. Well, under abnormal conditions or extreme conditions, we run into situations that could be exploited by somebody. Okay? I happened to be in Boston that night, which made everybody start asking me lots of weird questions. So, I actually was sitting with a gentleman from the NSA when it happened. His phone and my phone went off at almost exactly the same time. And everybody was like, what's going on? So that was kind of interesting. But physical safeguards are nice because you fundamentally cannot hack them. You can't hack them remotely, at least, right? But I'll tell people, remember, let's say you have a one-way check valve that would prevent you from being able to backflow material into a pipeline or something like that, okay? Well, even that one-way check valve is there and say fundamentally you can't hack it, well, what does that do? Do you actually remove the risk, right? The threat is putting material backwards into the pipeline. If you put a physical safeguard there, have you removed the risk of actually that happening? No, you haven't. You've just transferred it somewhere else. Right? So one thing in security I always make people mindful of is when you mitigate a threat here, where do you move it to? You don't ever actually get rid of it. You just move it now into fraud and collusion or some other type of human intervention or some other type of attack. So you always need to be mindful of, we can't just say we've mitigated our threat, we've mitigated the risk. You cannot do that. Because all you've done is take it from one spot and put it somewhere else. And if you're not mindful of where you put it, you can find yourself in trouble. And this is where the physical safeguards really come into place. So a mechanical trip or a one-way check valve or something like that may be an ideal physical control, but now I've transferred the risk into fraud and collusion. So, for example, getting into labor negotiations or things like that. You run into situations where people are quite willing to compromise the system to impact the way they want, the outcome they desire. So again, you've got to start thinking about these things in a process environment to go, hey, where did I move risk to? Okay. Then we get into safety intermittent systems. Now, so the diagram there, if you look, it kind of moves up through there. The process control layer, that's your PLCs, the safety layer. Those are your emergency shutdown systems, your safety intermittent systems, some of those soft interlocks. And then you really get into, what are some of the other physical safeguards and man traps and blast walls and berms and containment systems, right? So in other words, these are, what are they? Engineered layers of protection, okay? Now, this is all done mainly from the safety side. Now, what I want people to start thinking about, though, is let's break our safety thinking out a little bit and start thinking cyber as well, because there's lots of places a safety intermittent system would be a really good solution to a potential impact, but we don't use it, and you're going to soon see why, okay? Coming to terms of terms, I'm just going to hit this really fast. PSM, Process Safety Management, HAZOP, Hazard and Operability Study, BPCS, that's a term we use a lot. We're talking about safety to distinguish between process control and safety systems, basic process control systems. I don't care, PLC, DCS, I don't care. Okay, that separation of SCADA versus DCS versus controller, by and large, is only academic, right? We make controllers just as powerful as DCS systems now. So don't get tied up into that too much. BPCS works pretty well in this terminology. LOPA, layer of protection analysis. How many layers and safeguards do we have? Safety instrumented systems, safety instrumented function, or the SIF. Okay, that's actually important. So SIF is like, if pressure temperature 1 is greater than 102, then implement the ESD function, right? Those are fairly simple logic. PHA, process hazards analysis. Okay. Types of safeguards, I always like this. Whenever I see the people, the safety thing, I always think that, safety third. That's one of my favorites. But, okay. Types of safeguards. Physical. These are barriers, berms, blast shields, man traps, protective equipment, right? For example, do we go into the control room, or do we go into where the control rods are in a nuclear facility? No, we don't. We have layers of protection between us and that. We don't move them in and out ourselves, right? Too dangerous. We have layers of protection between us and the process. Engineered physical safeguards. These are the one-way check valves, mechanical burst disc, mechanical trips. Mechanical overspeed protection devices are one I'm really, for rotational equipment like turbine gas compressors or turbine generators and things like that. Here's where I'm going to throw the first little rock. You look at what they're producing out there these days. They're all digital systems now. They're not doing mechanical overspeed protection in turbine gas compressors or turbine generators anymore. And like, oh yeah, it's perfectly safe, right? That's where there's myself and some folks in this room I think would be happy to challenge that. So something to be mindful of. Now, if you say, all right, fine, the only system we have now going forward is digital. Oh, well, it's not connected. Yes, it is. It's connected somehow, right? It's all connected. Don't ever tell me something's disconnected. I will take you to task on it, okay? There's always a way, right? Stuxnet proved that, Trisys proved that, several other things. So, okay. Either way, whenever I'm looking at rotational equipment, I'm looking at now, all right, fine. So these are the systems out there. We have to make sure that we protect them very, very heavily, because if somebody can change the parameters and say, hey, it's now safe to run at 100 RPM and then 3,000, it's perfectly fine, right? Not a really good idea, probably. It's going to eventually cause problems. But if I tell that system that's okay, it's never going to shut down, right? And then we get, soft interlocks, sorry, I skipped a little bit. Soft interlocks, again, those are conditions inside the controller, and then safety instrumented systems. Now, why do I break those out? Safety instrumented systems are like a very robust and much more expensive version of the controllers you're probably familiar with. So they're not very cost effective to use for every control function. That's the main problem with them. You don't see SIS a lot of places. The only place you really found it, regulated industries, where plants have opted for, or where plants have opted for very robust protection. In OSHA, there's the 1910.110J, if I remember correct, defines the parameters for mechanical integrity. So one thing you'll find out is, like, in the United States, it's OSHA and MSHA. In Canada, I think it's also OSHA and MSHA still. Outside the U.S., there's going to be equivalent organizations. So I'm just using that as one example. But I don't want to list all of them here today. What we found out in OSHA, they took a look at the standards ISA 84, 61508, and 61511, and they said, for your regulatory component of being safe, if you implement per these standards, 84, 61508, et cetera, you will be compliant with OSHA. Okay, so we have kind of a de facto regulatory requirement as a result of that. So like in the U.S., OSHA and MSHA, and outside the U.S., different organizations, you do have a requirement to be safe, but it does not necessarily mean you have to do it, the 61508, 84, you don't necessarily have to do it that way. Okay, those are just one way of achieving that compliance. The function of SIS, you said, again, in other words, you're not going to see them everywhere. The only place you're going to see them is where they've taken a look at the process itself, and through cause and effect and HAZOPs and all those practices, they've said the probability of failure here is too high, so we're going to put additional controls in to monitor the process to get us down to the probability of occurrence low enough that we want for it to be. It's a math equation, right? Non-deterministic. It is a threat that we really can't predict. We know that the failure is coming out there, but it has nothing to do with security. That probability has nothing to do with security. Don't let that trip you up. All right? Function of SIS, that determines the function of the SIS, and to what level it must perform is determined by those different practices. The goal is to reduce the frequency of failure and likelihood of impact to target levels, primarily guarding against entropic hardware fault again. So I'm going to talk a little bit here about the convergence of safety and security. This is where they come together. Because in cybersecurity, we are dealing with the same worst case scenarios. We have additional impacts we also look at, but we're trying to prevent, in the industrial cybersecurity world, we're trying to prevent the exact same impacts, okay? The risk equation, risk is what? Risk equals likelihood times consequence, right? We're dealing with the same consequences from a worst case scenario perspective. It's the likelihood component that's different, all right? So in safety, they're just going to measure, oh, it's just here's how often it's going to happen. In security, we're saying here's how likely it is that I'm going to make it happen, right? That's what we need to start working on, getting those two pieces together. Key components, the safety instrumented function, the safety builder. This one's key and critical. The safety builder is just like an engineering workstation. Engineering workstation is where we put our programs in and all this kind of stuff, right? The safety builder does the exact same thing for the safety instrumented system. And I run into a lot of places, here's the next rock, I run into a lot of places that put the safety builder and the engineering workstation on the same computer. You are giving the keys of the kingdom to somebody. Now, they have the ability to modify the safety instrumented function, and they have the ability to modify the process control, the process itself. Now, the interesting part, though, too, is I remind people with the safety systems, all you have to do is disable its functionality or give it a new tolerance, and then all you have to do is just wait. You don't actually have to hack the process. You just have to wait for an unsafe condition to occur, right? Remove the safety instrumented function. Okay. Okay, safety integrity levels. This is what we're talking about here on the probability. So if you look at SIL 1, the way safety works, they tried it this way. They tried to say, well, we'll make the vendors be more safe. They tried it that way for almost 11 years. They finally said that isn't going to work. We started doing the same thing in cybersecurity. Okay, we started saying we're going to make the vendors solve this problem, right? That's not really the right answer. It's not either or, it's both and. We all have a responsibility at the table to work on these things. But from the safety side, they finally went back to a model that said, no, you know what? Here's how safe we need to be in terms of reducing the likelihood of incidents within the plant. Now, how do we build a more robust process? And so we have various safety disciplines, and then we have safety instrumented systems. So we get into, you have the plant or the process will be rated to a certain SIL level, right? Safety integrity level 1 through 4. And then the controllers and the components and how you deploy them will be rated to a certain SIL level. And there's an entire practice around this in order to be able to define and then achieve the safety integrity level. Those processes are defined in 61508 and 61511 in detail, or IS-84 covers a lot of it as well. They cover all that material in great detail, okay? The SIL defined. So if you look at it, SIL 1, the safety availability is 99%. It is, what is that? It's 10 to the negative 8 to 10 to the negative 9 probability of failure per hour. I'm sorry, I went the wrong way. 1 is 10 to the negative 5 to 10 to the negative 6, all the way up to 4, which is 10 to the negative 8 to 10 to the negative 9, right? The probability of failure per hour. So if you establish that these machine components together, probability of failure per hour is outside of these tolerance windows, well, we've got a problem. We've got to do something to mitigate it down to the level at which we want to achieve. Logic, the logic project. Anybody been involved with the Logic, Automation Federation and Logic? Marty, don't raise your hand. So, anybody been involved with that? Okay. I had the ability, I was involved with it at phase 2 when we specifically were testing safety instrumented systems in various levels of integration. The reason for this is that right at that time, several of the vendors were starting to sell converged safety systems with the process control. They're still doing that today. This study found that was kind of a bad idea. I don't want to speak too much for it. You can read the results yourself. Andre, you can't raise your hand either, right? But they, by and large, found that this level of convergence was a bad idea. Now, as everything in the security world, it kind of depends. If you tell me this is the only way the solution is going to work, we'll find a way to make it relatively secure. But by and large, putting those safety systems together was pretty much a bad idea. And I think the Trisis malware that came out against the Triconic component is a really good example of why you don't want these things talking to each other in some way or another. You don't want your safety systems connected. Unfortunately, I find safety systems way too connected, way too much of the time. And I'm like, look, if I can get into the safety system either through fraud, collusion, or people there at the site, or even remotely, which I find remotely, unfortunately, way too often, and I can get in the engineering workstation. I've got all the keys to the kingdom. I can do anything I want at that point. I just need to understand the physics of the process, and I can cause all kinds of damage, right? And Trisis implemented all this in terms of malware. What's interesting is, again, this was actually at the beginning of when I started looking at safety systems heavily, and I found and wrote up this exact scenario in 2010 with a couple other folks. And we were by and large dismissed because they're like, no, they're not connected. It doesn't matter. Nobody's going to do that. Lo and behold, 8 years later, 7, 8 years later, it's implemented in malware, right? So yeah, you have to. This is something to be careful of. What's that? I don't know. Who knows? Well, unfortunately, there's a couple times it seems like that's happened. But I mean, but there again, a lot of us come to, we're looking at the same things at the same time. But you look at it. So the one thing I will say, the logic phase 2, we did a lot, and I've never found a way myself to cause a safety system, a modern safety system, to do what we call failing energized. Failing energized is bad. It means it says it's always true, and it's never going to implement its function. Now, I found plenty of ways to cause safety systems to fail closed. In other words, fail in a closed state. Well, in that particular case, what you're doing, the safety system is doing what it's supposed to do. It's supposed to go false and now implement the safety instrumented function. So, at that point, what have we created? Well, we call that nuisance trip, right? But no, so yeah, okay, I've created a nuisance trip. We're still going to stay in safe state, but I can still cause you a lot of problems if I implement that nuisance trip 10 times a day, right? I can still cause impact. But I've never found a way to fail when energized. They're really good. Modern ones are really, really good. But what we did find, and we found it in this study and what we found in things later, of course, was if I can get a hold of the firmware of the SIS and pull that firmware off the device, which I was able to force some debug ports open on some of those, pull the firmware off, and then put the firmware back on. And at that point, all it is reverse engineering programming exercise. Pull the firmware off, change it yourself, put it back on. You can bypass the safety system that way, right? Or get a hold of the safety builder. Get a hold of the safety builder, make the change there if you want, and then write it back. So in other words, from a cybersecurity standpoint in safety instrumented systems, the two main avenues of approach are going after the safety builder or going after the firmware of the device, both of which were actually implemented in TriSys. Okay? So to some level, were implemented in TriSys. So there's one of the reasons we really don't want you integrating these components. Now, I know there's some vendors that are doing it. We can have that discussion offline. I'm not calling anybody out now. There's different ways to do it. Okay? Result, the primary target of the SS, the firmware and the safety builder. This is the target, the TriSys malware, which we just talked about. And again, but that report is really good. There's actually some really good information out there, and you'll find. I mean, again, we found back then. It said, hey, integrating these systems is not necessarily the best idea. Doesn't mean you can't do it, but I will tell you, I was at a refinery in. Well, I'll leave the country out, so it might make it obvious. I was over in the Mediterranean. We'll leave it in that area. At a big refinery, and I compromised the facility within 11 minutes. Through a vendor website, their host IT provider had another customer of theirs that had a website they had ceased operation on, but it was still there and it was out of date. I used that. I got in through their IT service provider and then jumped all the way into the industrial control system because they really were not architected very well. Let's just leave it that way, right? And then I was on the safety systems a half an hour later. And I'm like, that right there, guys, that's all you need. That's all anybody needs. And now it's just a matter of time. Now it's just a matter of time before people implement all those different attacks. Okay. SIS, bottom line, they're not everywhere. So think about it for just a minute. If you run your cause and effect and you run your HAZOP and the calculation does not hit within one of those 4 levels of probability of failure per hour, you probably don't have a safety system. You're probably going to have maybe a soft interlock or something like that. Soft interlocks, it's just like changing logic in the PLC. If I can download the program and change it, I can change it myself. Changing set points, masking signals. Is Joe Weiss here? He talks heavily about the idea of going after the sensors. I'm a big proponent of that. I go right after the sensor, modify or change the values that are being sent back, change it from the switch. Do whatever you want to do, right? But that way I can actually input at a very low level, I can impact the process. And soft interlocks, if you really are using those and you have a truly dangerous process, you need to start thinking about upgrading that to another SIS. I've got several examples we could talk about, and if I run it with a minute, I'll give you 1 or 2. But yeah, again, there's plenty of places now that I will recommend SIS that the calculation didn't necessarily say it so, but I'm like, look, there's too much of a probability of failure. Like one example is a hydrocracker did recently, a few years ago now, ISO hydrocrackers. Component A, then component C at 7 minutes later, and then component D at 12 minutes later. They have to fail in that exact order at that exact time to cause a blow up, right? Well, that's not going to happen in nature. That's way too unlikely for that to happen exactly in nature. So there's not going to be any additional protections there. There'll be physical ones, but no more electronic ones. Well, from a deterministic threat or a cybersecurity threat, guess what? I know that blow-up path. I can implement that. So there's an example of where a digital system, where safety may not want it to be, safety may not say it needs to be placed in there, but cybersecurity does. Right? Hit this really quick. So some of those standards out there: ISA 84, 621.508, 621.511. In ISA IEC working groups, 62443, or what was previously known as ISA 99, We have working group 7. Then ISA 84 on the safety side has one working group 9. They're both dealing with cybersecurity of safety systems. There's the API 1173 for pipeline. OSHA and MSHA have 1910, 110J, and I don't know the equivalent one on the MSHA side anymore or outside the U.S. They're still really good references. If you're not from the U.S., you're going to have an equivalent in your country. Excuse me. But what about DHS, CFATS, NERC, SIP, NIST 882? Are those safety standards? Think about it just a minute, though. Okay? ICS and security and safety both share a common goal of preventing dangerous failures. Okay? Those standards, being cybersecurity standards, still have an implied component of when you're doing an analysis or a CVA, cyber vulnerability assessment of a process, and you're identifying dangerous failures. I like the last one on scanning those components. I loved your comment, man. The comment you made, Jason, on you may have a low here, but what if this low could be used to exploit a condition within the process that's actually very high? You cannot stop at the CVSS score. Okay, you can't stop there. In fact, actually, I actually, when I do a penetration test, I specifically avoid using any vulnerabilities. There's only like 1 or 2 I'll use to crack the case into the system. After that, I go native protocol. That's it. That's how I do pen testing. Okay, I don't like going after it because I'm like, I'll prove this point. I'm like, there's no point in the CVS stuff. I will be, once I'm on the system, it's over because I'm using stuff out there native to do it. Okay, so anyway, but we have common goals. So. Plenty of cases where the probability of failure from hardware perspective is too low for SIS, but for safety, for security, we want to put it in there anyway. So by and large, it's best not to connect them. Okay. So when evaluating, this is where I'm trying to wrap this up really quickly here. When evaluating, start if you're doing a CVA. Okay, this is trying to get you guys some idea. If you're doing a CVA or if somebody's doing a cyber vulnerability assessment for you, evaluate the cause and effect. Call them the C&Es. Evaluate the cause and effect diagrams. Usually it's a large spreadsheet. All right. PHA, process hazard analysis, HAZOPS. Look for those worst case scenarios. Look for those the maximum output scenario. And then look, say they're going to have a probability of hardware fault causing it. You need to look at that from a cybersecurity perspective and say, is there a cyber-directed failure I could direct at this as well that would cause the same thing to occur? That's how we get those two. That's the first step to getting those two disciplines together. Right? Look and see if you can cause one of those things to occur. You're going to find when you walk into a plant, you're going to find somebody that can do this. And if you guys have heard me before, I make this joke often. If I want to know how to blow up a plant, I go find the oldest, crustiest, grumpiest person I can find in the plant and ask him how he would blow the place up. And he or she will look at you, and they've probably been imagining scenarios for the last 30 years in their mind. You will get some really useful information really quickly. All right. Okay. Read with a security mindset, all right? Inspect the physical, mechanical, logical, and technical safeguards. There needs to be layers of protection. The people that go out there and say put a firewall in front of everything, I start raising my eyebrows really quickly. I'm like, okay, great, firewalls are good. They know how to do this, but they know how to do a lot of stuff. But they are only there to control the communications. They don't necessarily control some of the other stuff underneath that. Now I know there's technologies out there to do some cool stuff, and I use them all the time. But by and large, the firewall in front of everything is not going to or I don't care. Host intrusion detection, host intrusion prevention, EIEIO, super security plan of today. I don't care which vendor solution you pick out there. If it's just looking at the cybersecurity and the network communications, it's not looking at enough. Okay. Okay, so we have cyber physical systems. Respect all those. Beware of situations where dangerous failures are possible but not probable based upon SIL calculation. So if you still have a dangerous failure scenario, even if there's not an SIS, you need to ask questions about cybersecurity. Can I cause this to occur? Okay? Also be mindful of when you take risk away from one area, you move it somewhere else. Always remember that too, because I'm just changing it to a new threat vector. Okay? All right. Here. Key takeaway, soft interlocks and basic process control system may be insufficient. They are insufficient for safety. I say may here, but I'll say are to the rest of you, all right? Bad idea. If your safety strategy is based upon logic inside of a processor that somebody can download or change or mask set points or change sensors on, which that kind of stuff we do in the penetration testing and the hacking community all the time, you're asking for trouble. SIL calculations may fail to identify cyber scenarios where SIS may be beneficial. SIS can be a last line of defense, but must be isolated from the network to be reliable. So it's just a matter of good architecture. So, again, just because you can doesn't mean you should. That refinery I was talking about, I found the safety instrumented systems through a vendor-connected website. They had their own. They were there on site as embedded engineers. They had their own connection. I got sniffing around a little bit, found their own connection out, came back in, no protection, and guess what? I found the safety systems as well because they were connected to them so they could make changes to them because they didn't want to have to walk across the plant either. All right? Just because you can doesn't mean you should. So, okay. with that, any questions? Sure.
In the Triton case, Schneider made a big deal about the fact that the key should be turned to the don't make any changes position.
Yeah, the run. Yeah.
What do you think of that?
Okay, so that's a recommendation. I mean, all the way from back when we started this field, I was working at Rockwell. That was the first thing we always said was put it into the run state, right? Now, there's a couple problems. It's really easy to make that recommendation. Two problems. Number one, we've been able to override those conditions in a lot of different controllers and say, I'm not making a comment about any particular system, but I've been able to override those conditions quite a bit in some of those. Not all of them have those switches as well. Plus, the most dangerous part about being in a refinery is being in the refinery, okay? So nobody wants to go out there. And if they say, it's like, look, that's too dangerous of an area, it's really not a good idea to send people out there constantly to make changes because it's too risky to the people. They may want to leave those in remote program mode for good reason. So it's not a panacea. It doesn't stop everything. But the main things to be mindful of is we can override those a lot of times. And like I said, the other one is there may be a really good safety reason why people do that.
And
right?
override them in software?
Yes.
Okay. Sorry to cut you off, Brian.
No problem. We're good.
All right.
Thanks.
Excellent. All right. Thank you so much, Brian.